Okay, so the exams I will have graded by Friday. Your scores will be up by Friday, exam 3. What we have left is exam 4. That's going to be our scheduled finals time. And I guess I keep forgetting to look. I think someone said it's Thursday, but I better post that on D2L. But I think it's maybe Thursday early in the morning, 8 a.m. And this exam is going to have only one topic. The problems are going to be relatively simple because we won't have had much time to work on this stuff. But it's going to be on the energy method for solving linkages. And so we're going to finish talking about that today. And then the exam is going to be in a week. There's also a third problem set that's posted right now. And that's due by Friday, 5, is that the 12th? Friday is the, oh yeah, right. And that has some linkage stuff and some rotating coordinate system stuff. Other than that, I don't think we haven't done any problems that have combined those two topics, but other than that, there's nothing unusual about it, nothing tricky or anything. Yep.
Where do we turn it in?
Oh, yeah. So you can turn in a hard copy if you have it done by, like say if you have it done by Thursday, you can turn it in at the exam. Otherwise, there's a D2L Dropbox for it. No, it's a linkage in the using the Newton's approach, Newton's laws approach, and then you also have to do a rotating coordinate system kinematics thing with it. So it's bringing those two concepts together. There's no energy stuff on it. Don't put it on the D2L Dropbox. Put it in the D2L Dropbox. Any questions about the end of the semester? How this is? Okay. No, it's not. It's using the old stuff. It's using the last two old things. Newton's laws, and then there's a rotating coordinate system thing. Oh, the final, yes, the exam is on energy approach to linkages. And that's the only thing on it. And because we have so little time, we've spent so little time on it, it's going to be even more like the practice problems and example problems than you're used to. It'll be something that we've done in class or something in the practice problems, basically just with numbers changed. Okay, so high correlation between doing those practice problems and going through the example problems and doing well on this test. Okay. No, right. That's right. By the way, this is my last, you guys are going to be the last time I ever give a test in a finals period that doesn't have a cumulative part on it, so. That's right. It's all, yeah, so I think what I'm going to do in the future is have a portion that's cumulative and then a portion that's on. You know, I get 3 hours. Why waste it? All right. Anyone have any questions about the stuff we're working on now? Okay, so we're talking about an energy approach to linkages. Energy approaches are kind of cool because you can figure out all this information that has directions using an equation that has no direction associated with it. Seems odd, surprising kind of, but the fact that you don't have to do vector stuff is one of the strengths of energy methods. Okay, and this energy approach uses the work energy principle, which says add up all the work on the linkage or the connection of things. And that gives you the change in total kinetic energy of the linkage. This actually is true for more than linkages, but it's most useful for linkages and sets of rigid bodies. And last time we talked about how to calculate kinetic energy. Well, first, so just jog your memories. The first thing we did was sort of, I presented an argument for why this is especially good for linkages. You might remember that was the part where you weren't paying attention because you're like, this isn't going to be on the test. But I think it's useful background, you know, like, why are we going in the linkage direction? Well, it's especially good for linkages. And I talked about why that was. And that had to do with work. Okay, that has to do with where work is zero. What kind of forces do zero work? And then after that, I went into talking about how to calculate the kinetic energy. Okay, so we're going to finish talking about kinetic energy. We're just doing one problem. We've talked about all you need to know for that. And then we'll go into how to calculate work. And once you have those two things, you know how to do these problems. The trick to these problems, though, is always coming up with the geometric constraints. So I'll mention where some good places to look for, where some good places to start trying to find these geometric constraints. Okay, so the example that I presented at the end of last time that we didn't solve was a linkage with a pin joint down here, and a pin joint connects it to a horizontal member. That I did it as rollers on a wall, but really let's think of it as confined. You know, rollers on the wall could fall away from the wall. I want to make it clear that this thing is going to stay sliding along that vertical line. Okay, and so we're going to call this member 1, this member 2. I'll call this joint A, B, and C. And we'll assume that the angular velocity for omega 1 is 5 radians per second. The mass of 1 and the mass of 2 are both the same, 10 kilograms. And we're going to think about this. You know, there's no coordinate system implied with energy methods, but in order to calculate the work and kinetic energies and stuff, you usually have to just choose a coordinate system, even though the numbers would come out exactly the same no matter what coordinate system you choose. So that's the one I'm going to use, standard coordinate system. And we want to know what's the total kinetic energy for the linkage. And so I'm going to first define the kinetic energy just using the rules that I said for kinetic energy, but I'm going to define as many variables as I need. I'm not going to worry about how many variables I have. Then afterwards, I'm going to think about going back and coming up with constraints between those variables. Okay, like for example, the kinetic energy of member 1 here, that doesn't have a fixed point. So we have to use a translational kinetic energy plus a rotational kinetic energy. Obviously, the rotational and the kinetic energy are related in some way, right? But I'm not going to worry about that at first. I'm going to come back to that and deal with it with a constraint equation. Okay, so first calculate the kinetic energy of body 1. There's no fixed point. So the kinetic energy is equal to 1/2 times the moment of inertia about the center of mass times omega 1 squared plus 1/2 times the mass of the object times the velocity at the center of mass, I'll say of 1 squared. I guess both of these centers of mass, just to be clear, I'll put the 1 on there. Okay, and some of these things we can put numbers to, some we can't yet. The moment of inertia of 1 about the center of mass, we'll call this a slender rod, so this is 1/12 times the mass times the length squared. And so you get 0.833 kilogram meters squared. And so, yes, I meant to say that. So yeah, both of these lengths are 1 meter. Okay, so the kinetic energy of body 1 is 0.833 times 1/2 times omega 1 we know is 5 radians per second, so times 5 squared. That's the rotational kinetic energy. The translational kinetic energy is 5 VCOM1 squared. And the mass is 10, so I already did that. So we have 10.4167. What are the units? So joules, right? This is work, so SI units are joules. So 5 VCOM1 squared. And now we'll go on to the kinetic energy of body 2. Does this one have a fixed point? Yep, that pin. So this time we're going to say the kinetic energy of body 2 is just equal to 1/2 times the moment of inertia about the pin times omega 2 squared. The moment of inertia about the pin is equal to 1/12 times the mass times the length squared. And then what else do we have to do? Yep. Yeah, right. Parallel axis theorem. So that's the mass times what distance squared? 0.5 from the center of mass to the fixed point. So 0.5 squared. And so you get a moment of inertia for this body of 3.333 kilogram meters squared. So T2 is equal to 1/2 times, I guess I'll combine that. So 1/2 times 3.33 is 1.667 omega 2 squared. So the total kinetic energy is equal to 10.4167. You're just adding up all the kinetic energies of the individual members, plus 5 VCOM1 squared, plus 1.667 omega 2 squared. Okay, but if you look at this object, any one angular velocity determines all the velocities and angular velocities. Do you see that? If this thing, like if you move this thing, you move member 2, there's only one thing member 1 can do, and vice versa. Okay? This system is totally constrained, which means we shouldn't have to have any variables in our expression for kinetic energy. So now we're going to look for those constraint equations. Okay? And okay, so let me write this. You shouldn't have any variables, though, because knowing omega 1 means that you should know omega 2 and VCOM 1. Okay. So how are we going to do this? So for our constraints, we're going to do it the same way that we did it for the linkage problem set, and the same way we did constraints for any of those linkages. We're going to use the relative motion equations. And we're going to use them with so actually that position 1 is the position relative motion equation. Let me write this in a more organized way. So the relative motion equations that we're going to use are going to be the position of A is equal to the position of B plus the position of A relative to B. Okay? You can think of that as this is relative to the origin, this is relative to the origin. And the velocity relative motion equation says the velocity of some point A in our coordinate system is equal to the velocity of some point B relative to our coordinate system plus the velocity of A relative to B. Okay? And we're going to use that with the velocity of some point A relative to B, okay, is equal to omega of the body crossed with an r vector going to A from B, and that's all. Okay, so those are the same ones that we used for linkages with Newton's laws. Okay, so what I'm going to do is I'm going to start at the pin. Yep. Yes, that's right. So you can start with either direction. I'm going to start with C because we know the velocity there is 0. Use that to calculate the velocity of B, and then use that and the known angular velocity of member 1 to calculate the velocity of the center of mass. Yep.
So those A's and B's you have are just like...
Those are arbitrary, yeah. Oh, I see. I see why you asked that. Yeah, these... In this case, yeah. And what we want is the velocity of the center of mass of 1. So we're going to find the velocity of B relative to the origin, and then we're going to add it to the velocity of yeah, of the center of mass of 1, given that we know the velocity of b. Okay, so the velocity vector at b is equal to 0, 0, omega 2 crossed with an r vector going from c to b. So what's that vector? If we're going to b from c, what's the r vector? Yep. So calculate that, and, well, so this is negative omega 2, 0, 0. You can think of that as the velocity of b relative to the origin. And so now we want the velocity of the center of mass of 1 relative to b. Okay, that's going to be negative omega 2, 0, 0 plus 0, 0, omega 1 crossed with the r vector that points to the center of mass of 1 from b. So what would that vector be? Yeah, in the x direction, and then 0, 0. So combine all that, and you get negative omega 2, negative 5, 0. No, not 5. Negative. So this thing, this omega 1, is 0, 0, 5. And so if you do that calculation, you get negative 2.5, right? So that's an expression for the velocity of the center of mass, but it doesn't give us a constraint equation yet, really. I mean, I guess it gives us, so now we could calculate the speed of the center of mass of 1 as this thing dotted with itself. So we get omega 2 squared plus, what's that? What's 25 squared? 225? What's 25 squared? Oh, yeah, you're right. 625. Okay, so what we have now is, so that's one constraint equation, okay? We have one of our variables in terms of the other two, okay? But now we still have this expression for, so like if you think of updating the total kinetic energy, we would now have 10.4167 plus 5 times omega squared plus 625. Change this up here, by the way, sorry. When you take the dot product of those two, that gives you VCOM squared. You see what I mean? In this equation, I just wrote something down here that was wrong about dotting this. So 625, this whole thing I'm substituting in for VCOM1. Who's with me? Who's lost? Okay, you're trying to find the speed squared, okay? And, you know, the length of a vector is the square root of it's the square root of the dot product of the vector with itself. And so the speed, the magnitude squared is just the dot product with itself. So if you have something in vector form, this is just a way to get the magnitude squared. Okay. And then finally, we have, where is it? This, 1.667 omega 2 squared. Okay. So we're a step closer. Now we only have one variable instead of two, but we need one more constraint equation. So where's that constraint equation going to come from? Well, actually, we can use it again from velocities. We're just going to come up with an expression for the velocity of the rollers at A. And then we know that those rollers aren't allowed to have any x velocity, okay? Because they're confined to just move in that vertical direction. So our constraint 2 says the velocity at A, the velocity vector at A, is equal to the velocity vector at B plus omega 1 crossed with, this time, negative 1, 0, 0. Okay? Yep. This is 625, I think. This one? 6.25. Okay, any questions about this relationship? And then what I'm going to do is I'm going to use the fact that VA x component has to be equal to 0. Okay, so VA vector is our VB from before, negative omega 2 zeros, plus 0, 0, 5, because we know omega 1, crossed with negative 1, 0, 0. And if you calculate that, you get negative omega 2, negative 5, 0. Our criterion that says the x component of VA is equal to 0 now tells us that negative omega 2 is equal to 0. Okay, so first, any questions about the math, where the constraint equation came from? Okay, now we have to think, or we don't have to, but it's always a good idea to think, does that make sense? We have one of those two members with an angular velocity and the other one without an angular velocity. Does it make sense in this case? Yeah, it does. Instantaneously, if this is moving up and down, that motion is instantaneously independent of this thing. Like this, for this to move instantaneously up and down, that's tangent to a circle around B. Okay, so just at this instant, if I would have drawn it in any other position, we'd get some angular velocity for omega 2, and that it wouldn't make anything any harder. We just get a different value. But in this case, we got 0. So now we plug 0 in for all those omega 2s.
It's only because your R vector is negative 1 without a y component,
Right.
right? It would have a y component. If it had a y component, then
That's right. That's right. Exactly. And So plug this fact now into here, update, and you get that the total kinetic energy is equal to 10.4167 plus 5 times 6.25, and you get 41.667 joules. Okay. You're going to have to do, on all these problems, you're going to have to do some of that stuff. And in some cases, you can save yourself some work by sort of thinking about it. You can figure out some of these relationships due to symmetry and whatever. But I would recommend, don't get too cute about it. Like you won't ever have big time constraints on this test. And if you ever have to do real problems with this stuff, you won't have any time constraints, like you can stay up another hour or whatever and do it right. So I would recommend getting used to doing it in the vector, with this vector approach, with this relative motion approach. Okay. So now we have to talk about how to calculate work. It's the only thing left to calculate because the work energy principle just equates work with kinetic energy. And this is, if you go back to last class, I said that calculating the kinetic energy was going to be sort of our topic 1. So this is our topic 2. And we can break this up into work produced by a force. The definition is the integral from location 1 to location 2 of the force vector dotted with the incremental change in position. You might remember this is called the line integral. In most cases, we won't have to do this integral. In fact, in this class, you won't ever have to do any of these integrals, but that's the definition. When would you have to use an integral, and when could you just calculate it algebraically so you can simplify this to f dot p2 minus p1 when, finish this sentence, it's like a nerdy Mad Lib. That actually, no, that not necessarily. So actually, it can be a curve in some cases, and you can still calculate it this way. And it can be a straight line, and you can't calculate it this way. What it has to do with is the nature of the force. And yeah, if it's a constant force, so yeah, that's right. When it's a constant force, the path doesn't matter. So in a gravitational field, which we always approximate as a constant force, right? The amount of work done to do a motion like this and end up here is the same as the amount of work to do this. Okay. When this is sort of an aside, we're not going to do ones like this, but when the force is conservative, You can always calculate the work as the change in potential energy. By the way, that's a good thing to keep in mind. Why can't you do that when the force isn't conservative? That's kind of a nonsensical question because there's no such thing as potential energy except in conservative force fields. Okay. So you're out of luck. You got to do the integral if you're dealing with friction. What? Springs are conservative forces the way we usually treat them, unless you're dealing with friction and stuff like that. The two sort of most classic conservative forces that you do in physics classes have to do with springs and gravitational fields. Okay, that's enough about that. But in this class, for these problems, you're just going to use this one. Okay. So I'll put it in red. I don't want to say like this one's more important than the other ones because you have to think about the cases, but practically speaking, for the problems you're going to be doing, this is the only one you have to think about. Okay. And the second work calculation that we're going to have to do is the work of a couple. And that is the integral from some angular position theta 1 to theta 2 of the couple d theta. And again, you can calculate the work as the moment times theta 2 minus theta 1 when the couple is constant. This is 2D. Things get a little messy in 3D, but we're only going to do 2D problems this way. Any questions about either of those? There could be analogs to the one we just talked about, but there aren't too many practical examples of couple fields, you know, conservative couple fields and stuff. There's just nothing around us that does that. So pretty much this is the one you're going to deal with. Okay, so here's an example. Let's say we have a member like that, a member that's half as long, like that, that's connected to a slot. You following what I'm saying here? Okay, so if this arm moves, the right arm slides along that slot. If we call this member 1 and this member 2, and we'll call this A, B, I gotta move B because I'm gonna put a force there, B and C. This has a length of 1 meter. This has a length of half a meter. We have an external force acting down of 1,000 newtons. And this member 1 has a mass of 50 kilograms. Member 2 has a mass of 25 kilograms. We're going to include gravity. And the question is, what's the total work done on the linkage as H, and let's actually make H go all the way to the pin down here, up to the top pin. Okay, so as H goes from a height of 0.5 meters to 0.25 meters. Okay, so can you picture what the orientation of these members is going to be? So at these 2 points, when H is equal to 0.5 meters, what are those angles going to be? This is going to be 30, because this length is 1, right? So the sine of 30 is half. So it's going to be basically in the configuration it is here. And what about when this point B is at a height of 0.25? Like, you'd have to calculate that angle, and it wouldn't be too hard. But what's the angular position of, like, this one is going to be at some angle bigger than 0. What's the angle of this one going to be? It's actually going to be exactly 180 degrees, you know, because this height is 0.25. Did I say that? I have to say that. Otherwise, you don't know. Yeah, okay. Okay, so let's draw a free body diagram of this whole body. Just in some arbitrary position, and figure out what the loads are going to be acting on this. What's the type of force that's going to be acting at the pin? Force vector, yep. Call that RA. There's going to be a force of gravity on member 1 acting at the center of mass, 50 kilograms times 9.81, so this is 490.5. There's going to be a downward force of 1,000. There's going to be a force due to gravity at the center of this shorter member with a magnitude of 245.25. And then what type of force is acting at RB? Yep, just a force perpendicular to the slot. Yeah, calling that RB would not be a good idea. Okay, so let's set up some extra variables for now, and then we'll go back and do the constraint equation. So let's call this the height of the center of mass of 1. Let's call this one the height of the center of mass of 2. This one we're already calling H. And of these forces in the free body diagram, which ones produce work? Does the force at the pin do any work? No, because that point doesn't move. Okay. Does the gravitational force here do work? Yeah. Does the 1,000 Newton? Yep. 245? Yep. RC? No, because the motion is perpendicular to the force. Okay. And that's even true if it's just instantaneously perpendicular, although in this case, that motion, no matter where it goes, is perpendicular to the force everywhere. But that would even be true, if this was at the bottom of a circular slot, So we can set this up as the work total is equal to negative 490.5 times HCOM1, let's say at the end, at the second position, minus HCOM at the start, plus a downward force of 1,000. I'm just doing these as, you can also do these as a dot product, but this is what you would get from those dot products. Let me know if that's confusing, but times H at the end minus H at the start, and then plus negative 245.25 times the height of the center of mass of 2 at the end minus the height of the center of mass of 2 at the start. Okay, so the two that we know without thinking about any kind of constraints are H end and H start. Those are the ones that are given, right? H end is 0.25. H start is equal to 0.5. So you can update this as the total work is equal to negative 490.5 times H COM1 end minus H COM1 start plus, or take that, minus 245.25 times H COM2 end minus H COM2 start. And then this one gives you negative 1,000 times 0.25 minus 0.5. So that's just going to be adding 250. Does it make sense that that work should be, like, if you think about it physically, does it make sense that that should be a positive work? You have a feel for that? Remember what work means? So yeah, if the direction of the displacement vector and the direction of the force are in the same direction, then you have a positive work. And that's what's happening here. The thing is moving down, the force is down, so it's positive. It's adding energy to the system. Okay, so now we need to figure out what these values are. The heights of the other things at these values. It's just a trigonometry problem, right? So and I'm not going to, I have a couple things I still want to say, so I'm not going to go into a long calculation. But you could do as a trig problem, or you could calculate positions as, L cosine theta, L sine theta, and use the position of A, use the relative motion equation for position. PA over O is equal to PB over O plus PA over B. Okay, either of those two ways, you'll get the same thing. The answer you should get is I didn't finish it. Stupid. Okay, so let me just give you that. If you're going to do it this way, the theta at the starting point is 30 degrees. The theta at the ending point is 14.478 degrees. And if you plug this, if you use this with the trigonometry, the relative motion equations, for which one? That can be the approach for both of them. Oh, I see what you mean. The angle. No, the angles are different. Yeah, thank you. That is for number one. So that's the theta. Yep. Okay, so we're just looking at a free body diagram of the whole thing, right? And so if you do a free body diagram of the whole structure, then you're not worried about internal loads. But then the real question is, why are we allowed to do this, given that that the works of those internal loads don't necessarily come out to be zero? And that's what we talked about last time. It turns out that what happens to pieces inside rigid bodies and what happens at pins of rigid bodies is those internal forces do zero work because the objects move together. And you might want to just glance back at your notes from last time, because that's a good thing to, I think, store with this information, And so yeah, the free body diagram doesn't show the internal loads because it's a free body diagram of the whole thing, and those are internal. But the important thing is, the reason I chose a free body diagram of the whole thing is because of the types of forces that do zero work. Yep.
RC doesn't work because all the weights are perpendicular to allow motion.
It's actually, it doesn't have anything to do with what kind of loading we have. No matter what kind of loading we have, even if I put a force going this way, okay, the work is calculated by the force times the displacement at the location where the force is applied. Okay, so if I put a force going horizontally at the center of this member, okay, we'd have to have a work term that dealt with the horizontal displacement of this point. But at this pin, this type of joint can only support upward forces. Okay, so its instantaneous displacement is always horizontal, but its instantaneous force is always vertical. And so no work is done here, no matter what other forces are happening somewhere else. Okay, so yeah, that's an important thing about work. Like, I gave you this, and I think I, maybe could have made that more clear when we did this, when I defined work. So what we're talking about here is the force at a point and the displacement of that point. Okay? Probably worth writing in here. This is the motion of that point. Yeah, and it's a dot product. So if you do it as vectors, it'll come out telling you that. But yeah, it's a projection. Yeah. You have another? Okay. Yep. Any other questions? Okay, so let me give 3 general comments about using the work energy principle and this energy approach. About the work energy principle. The first is that using the work energy principle always relates a velocity variable like a speed or an angular velocity or some combination of these things to a position variable. Which would be like, you know, some kind of like a distance, an angle. Okay, that's different from what you get from Newton's laws. Newton's laws always relate an acceleration variable to time, because you find something at an instant and then you integrate through the instance to calculate the total motion, you know. So that's a fundamental difference, and that's why like you probably just sort of do this naturally, but if you were taking some physics standardized test and you had a problem where you had a skier at the top of the hill and they asked you how fast he was going at the bottom, you've probably just seen enough of these problems that you're like, oh yeah, that's sort of a classic example of conservation of energy, which is the work energy principle. So you know to use that. But why is that the most efficient way? Well, I think the best answer to that is this problem is asking you to relate a speed variable, a velocity variable, how fast he's going, with a position variable, where he is, what he's at the bottom. Even if you were given the shape of this hill, or even if it was flat or whatever, you could calculate an acceleration at every instant, but then you'd have to integrate to get that velocity. You know what I mean? So those are the kind of things to look at when you're thinking, how do I want to approach a problem? You know, two different linkage problems. When is it better to use this one or this one? It sort of has to do with how you want your information organized. You know. Any questions about that? Second, the work energy principle is only one equation. You almost always are going to need constraint equations to limit the number, you know, to reduce the number of variables. I'll call them geometric constraints. And finding those is almost always the trickiest part of these kind of problems. And then a third thing, so these are the two most important, but I think it's worth pointing out that if you want to find an acceleration, often you can. So once you find your velocity variable as a function of a position variable, you can often find accelerations, if that's what you want, using the chain rule, that same approach to the chain rule that we used when we first talked about particle kinematics. So as an example of that, if you know a velocity vector as a function of x, then the acceleration vector is the derivative, the x derivative of the velocity times dx dt. And you can set it up like that. So that's something to consider in some cases if you need to calculate an acceleration and everything else in the problem is pointing you towards an energy approach. You also you could also do it as, analogously. If you know an angular velocity is a function of an angle, then the angular acceleration is d omega d theta times d theta dt, and that is d omega d theta times omega. Any questions about that? Okay, let's try to get through a quick problem. Okay, so say that you have this linkage. Each member is 1 meter, 10 kilograms. What? Oh, yeah. Thank you. Yeah, that's a pretty uninteresting dynamics problem, the way I drew it. That's a roller. Let's go A, B, C, 1, 2. And let's say that there's a downward force of 2,000 newtons. And we want to know if this started at a height. Okay, so let's call this D. Okay. So the start height is with D equal to 0.866, like this is at 60 degrees. What's the speed at the roller B as a function of D? So this is the form that ideally you should look at this and say, okay, it's a linkage, it's calculating a velocity as a function of a position. All those signs point to using an energy method for this problem. Okay. Next week, on Thursday, how will you know like what problems to approach using an energy method? All of them are energy methods. Yes, that's right. Okay, so the total work, well, let's draw a free body diagram. So there's a downward force of 2,000 newtons. There's a force here, FA. This one's a roller, so we know the direction of that force, FB. And then there is 98.1 newtons down there, 98.1 newtons down there. Let's call this point D and this point E. So first, let's calculate the work. That's equal to, okay, so first, this one isn't going to do any work. This one isn't going to do any work. This one, and this one, those all are, right? What? Yeah, so no. With this kind of thing, I mean, that way of drawing it suggests that it's going to move smoothly, you know. If a problem is drawn like this, it always, then that means you're not thinking about stuff like that. There'd have to be more information given to tell you that that's a concern of yours. Okay. So the work is equal to negative 98.1 times the height of D at the end minus the height of D at the start minus 2,000 times D at the end, which is just our variable D, minus the start height, which was 0.866, and then minus 98.1 times H E end minus H E start. Okay, so what about the constraint equations? Well, the geometry is pretty simple in this case. This is an isosceles triangle. So this angle is always going to be equal to this angle, right? We're going to use that, I guess, later. This height is always going to be half of this height. And these two heights are always going to be the same. So our constraints for the work say that HD end is equal to HE end, which is equal to D over 2. And HD start is equal to HE start is equal to half of 0.866, so 0.433. So the work is equal to negative 98.1 times D over 2 minus 0.433 minus 2,000 times D minus 0.866 minus 98.1 times D over 2 minus 0.433. So you can rewrite that as negative 98.1 times D minus 0.866 and then minus 2000 times D minus 0.866. And now the kinetic energy. First, let's do the kinetic energy of body 1. That one has, does it have a fixed point? Yeah, so that's going to be 1/2 times the moment of inertia about A times angular velocity of 1 squared. So that's 1/2 times 3.33 times omega 1 squared. Kinetic energy of 2 is equal to 1/2 of the moment of inertia about the center of mass times omega 2 squared plus 1/2 times the mass times the velocity of the center of mass 2 squared. So the total kinetic energy is equal to 1.667 omega 1 squared plus 1 4. So this is, I think, 0.4167 omega 2 squared plus 5v COM2 squared. And now let's think about the constraints. So this is an isosceles triangle. These two angles have to be the same, which means if this one has an angular velocity of 6, what does this one have to be? -6, actually, but yeah, same magnitude. So omega 1 is equal to negative omega 2. Also, the velocity of the center of mass of 2 has to be equal to 1 times the cosine of theta sine of theta plus 1/2 times the cosine of theta negative 1/2 times the sine of theta. That's the position. So the velocity, you can take the derivative. This might have been a little bit faster to do using the velocity relative motion equations, but this is the way I thought to do it. So just take the derivatives. And so you get omega 1 times cosine theta. No. This is negative omega 1 times the sine of theta. Positive omega 1 times the cosine of theta. Plus negative 0.5 omega 1 times the cosine of theta, negative 0.5 omega 1 times the sine of theta. And so you get negative 1.5 omega 1 sine theta positive 0.5 omega 1 cosine of theta. Sorry, I know I'm going over, but I'm almost done with this. And then now that we have this stuff expressed in terms of theta, let's relate d to theta. So d is equal to 0.866 minus sine of theta. So as you're going through this, you should just look at the geometry and make sure that makes sense, or make sure that you understand a way that you could come up with these constraint equations. And so you end up with work energy principle that says, I guess, you end up with the speed in the x direction of that point B being equal to 2 sine theta times the square root of 258.16 minus 298.1 sine theta divided by 2.708 plus 5 sine squared theta. Yep. Yes, thank you. Yep, this should be sine and cosine. Okay, any questions about that? Okay, well, please come talk to me if you would like help making sense out of this. I'll check and make sure the practice problems are up for this. If they're not, I'll get them up right now. Okay.